All right, thank you everyone. Thank you for joining us tonight. I'm Skylar Tibbetts. I'm faculty in the Department of Architecture here, and I have the great pleasure of introducing Melodie and Julian. They're inspirations for many of us. Their work, many of us know and has been recognized around the world. We see their work in studios, and then more recently it's been a pleasure that we've gotten to collaborate, and they've been sort of co-conspirators with us on the space architecture work that we've been doing. So it's really a pleasure for me to be able to introduce them. So I'll start with Melodie. Melodie Yashar is the Vice President of Building Design and Performance at ICON. Melodie oversees the architecture direction of ICON's built work and the performance of its building systems. In prior roles, Melodie was a senior research associate with the Human Systems Integration Division at NASA. She was co-founder of Space Exploration Architecture, a NASA-funded research practice developing human-supporting design concepts for space exploration. Melodie was a professor of Pratt Institute and continues to teach at Art Center College of Design. And she received a Master's of Architecture from Columbia and a Master's of Human-Computer Interaction from Carnegie Mellon. And Julian Ocampo is a Senior Director of Design Build team at ICON, where he leads the design of the company's construction projects. His work integrates architectural design with advanced construction technologies to improve the speed, efficiency, quality of building processes. And prior to joining ICON, Julian was at BIG, where he led projects in collaboration with NASA on their habitat designs for Project Olympus. And he's contributed to the design of the Mars Duna Alpha Martian simulation habitat built at NASA's Johnson Space Center, and maybe most interestingly or importantly, alum of our program, the MArch here. So it's amazing to have both of you, and let's welcome Julian and Melodie tonight. Thank you so much for being here.
Hi, everyone. My name is Melodie. Thank you, Skylar, for the introduction, and thank you for the invitation to be with you all tonight. We'll give a little bit of we'll try to intersperse a little bit about my personal experience and Julian's personal experience and how we sort of arrived to where we are, working on large-scale additive manufacturing with ICON. And yeah, so title of the presentation is ICON and Large-Scale Additive Construction, Building on Earth and Other Worlds. The important thing here being that ICON is a large-scale additive manufacturing provider. We approach our work as robotics as a service to our customers, and in the last several years we've explored various, I guess you could say, modalities of working with others. We started out being a hardware provider, acting as a sub to large builders and contractors. More recently, we are a design builder, and essentially the full scope of design from architecture through construction is under our purview. And even more ambitious than that, we've also started acting as a developer, purchasing our own lands and building and constructing homes that can be sold directly to consumers. We do all of this by being vertically integrated. So as a construction technologies company, we develop our own robotics in-house, we develop our own software in-house, proprietary materials in-house, and then our own architecture in-house. This is a very unique multidisciplinary environment, quite different from other large-scale additive manufacturing providers in industry right now, and it enables us full scope and full authorship over what it is that we're both designing and building. Importantly, ICON was really co-founded by 3 individuals to address what we believe is a global housing crisis. We really think that the housing of the future should be different from the housing we have known. And of the many benefits that automated construction can bring, the one that was most salient to the co-founders was that of introducing rapid growth within the housing sector. And so you'll see the form factors of our printer in particular started out as particularly optimized for single-family detached housing. And so we look to additive construction, we look to autonomous construction as a way of introducing efficiency in construction processes that you don't get from traditional means and methods and from traditional labor. This is something that we really play towards, and that we continue to advance in our work. What we like to say is that it's been sticks and bricks for hundreds of years, but everything is about to change. Unlike traditional flat pack, mass-produced building construction materials and systems that need to arrive or be transported from a factory onto site, we focus almost exclusively on on-site construction using additive manufacturing. So we mobilize our printer to the site, we mobilize our material handling system to the site, and basically do our construction that way. The other key advantage here and value add of additive manufacturing is that essentially we have this tremendous freedom of form that we can explore. I'll speak to that in just a second. But overwhelmingly what we've found is that as compared with standard materials and methods of construction like stick frame and concrete in particular, and masonry, we have overwhelming speed when we're 3D printing out on site. It introduces more affordable costs in the housing sector. We have a fully customizable system in the sense that, well, you all probably know, being a digitally native environment, you can essentially model and print anything within the realm of physics. So we play into that versatility to introduce customizability where we can. The printer is agnostic to what it prints, right? And so we really try to introduce benefit by playing on customizability where we can in our work. Because we're using a mortar-based concrete material, it is a highly, highly resilient system that we've developed. We play into that and take advantage of that to introduce a more durable system, which we believe has greater longevity than other materials and other methods of construction. And to me, it's another and a different way of thinking about sustainable construction. We're not building anticipating that there's going to be renovations happening within 3 to 4 years. We want to build architecture and we want to build homes and structures that can stand for the next 100 years. And this is just a different way, a different kind of outlook towards how it is that we're approaching design. Lastly, as high performance, the system maintains high thermal mass, and we use a lot less waste. We've encountered some metrics in construction that a single family home can produce up to like 2 or 3 tons of construction waste. And essentially, we only look to print as much material as we need for each build that we have. I mentioned the freedom of form. This is something extremely important to us from a design perspective. We're not interested in just duplicating architecture that looks and aesthetically basically is doing the same things as traditional construction. So we play into the capacity to create organic geometries, more eccentric shapes, and textures and patterns where we can. We've also investigated domed structures and how we can create more cantilevered geometries, which are more typical, I would say, of compression-based structures, less typical of stick frame. And this is something that we look to incorporate in our work in a way that, again, is cost-effective and efficient in construction. This is a quick, I guess you could say, this is a quick time lapse of what our terrestrial construction system looks like. You'll see that we're working with a gantry system. Essentially, it operates on rails. The limit of the gantry system currently is 12 feet tall. But essentially, we have been prototyping and working with this system as a way of advancing our on-site construction capabilities. That work has also been in support of advancing technology development for our in-space systems. Since ICON started, ICON has been a contributor and a thought leader in thinking about autonomous construction on other planets, particularly the Moon and Mars. And so we use our terrestrial work as a vehicle and as a way of advancing some of the essential technology development questions that are inherent in how you build on other worlds. And so roughly around 2020 timeframe, ICON started a collaboration with a NASA group referred to as the Moon to Mars Planetary Autonomous Construction Technologies Program. This is a group at NASA that's interested in using in situ materials, meaning local and indigenous materials, on the surface of the Moon and Mars to create various kinds of infrastructure. Over the course of a one-year-long collaboration where we pursued some architectural visions, which Julian will go into more detail about, and collaboration with various partners, both academic and in industry, ICON was awarded a $57 million Small Business Innovation Research Grant to essentially develop technologies that can one day be deployed on the surface of the Moon. In order to answer the question, what is the hardware that will one day 3D print on the Moon, we asked ourselves, well, what are the artifacts, what are the specimens, what's the infrastructure that this system would have to print? And so it became a kind of, I guess you could say, call and response investigation, where we, in order to determine what the hardware requirements were, we had to ask ourselves, well, what is the use case? What is the application of the technology? And so ICON took it upon ourselves, basically, to introduce design concepts for habitats, unpressurized shelters, and we're currently continuing to work on how we can develop horizontal construction types in support of the vision of 3D printing in space. This was all done without being asked by NASA. NASA didn't say, give us a vision for space architecture in space that can be 3D printed, but it's something that we took upon ourselves and that we felt it was important, really, in pursuing this question of what is the most essential infrastructure. And so pursuing various collaborations, we came up with designs and concepts for landing pads, blast shields, and habitats. And Julian will talk more about one of those. Around that same time, in ICON's facilities, we started messing around with weapons-grade lasers. And this is an example of a regolith test bed that we have in our headquarters in Austin. Essentially, what's happened is that the Olympus team, our off-space work is referred to as Project Olympus, has developed a robotic test bed where we have an end effector that is able to scoop, sieve, and process local regolith, which is basically the sand that you see here. This is a regolith simulant that we're working with, and sinter it onto itself, which is what you're seeing here as well. And then in successive layers, apply more material, level it out, scoop and sieve it, validate it for its properties, and then continue manufacturing whatever your artifact is. And so here's an image on the right of how we have an integrated scoop, tamp, and filtering system with this one end effector. And we're prototyping that within a small regolith test bed of simulant, but also developing a prototype for a larger robotic manipulator, which would be more along the scope and scale of what flight hardware might look like on the surface of the Moon. And in the last 6 months, the prototype robotic arm that you're seeing on the left was tested within the Large Dirty Vacuum Chamber at Marshall Space Flight Center to basically evaluate how it's going to perform and whether it can withstand lunar thermal vacuum conditions. We created this video to show what we feel is going to be the first demonstration mission with this system. Essentially, what we're looking to do is deploy the Olympus robotic arm aboard a generic CLIP-style mission, which is what you're seeing here. This is a CLIPS lander. The robotic manipulator would go ahead and scoop the local regolith, validate it for its mineralogy and its properties, create a level surface, such as you saw within the small robotic test bed, and then lays upon itself in successive layers to create the kind of infrastructure that we're most interested in. Our first demonstration mission is planned within the next 6 years, I would say, although we're not flight manifest right now. But the important thing is that the technology development has been happening steadily since 2020. And so our vision is that the first demonstration mission would be aboard a CLIPS lander. Eventually we'll go off lander to build extended volumes. And then finally we'll have a commercially scalable, habitat-capable system that can create large-scale infrastructure that can one day house human beings or crews on temporary missions. So a lot of the technology development was not in direct, let's say, did not directly impact and was not directly influenced by the architectural work and the vision that we put forward to NASA. However, when they saw that work, they immediately attached to it. And something really remarkable happened was that it's almost like you have to see it to believe it. Our vision and the vision that was put forward by the Bjarke Ingels group, who was a consultant to ICON at the time, as well as of space exploration architecture, was taken by NASA Space Technology Development Group, STMD, and then basically they assembled the roadmap for their own excavation and construction and outfitting capability development. So I can't stress enough the power of an architectural vision to synergize thought leadership about very difficult, very wicked ideas that are hard to imagine and that are hard to really see happening in the world. All of this work that we're imagining happening in space brings direct impact to how we advance our technology here on Earth. We did an exercise with the NASA team investigating how we can create shared technology development initiatives in both our residential construction work, the NASA in-space construction work, as well as for the Air Force and the DoD. Overwhelmingly, there are shared initiatives among the three. And so our thought here is, why not create dual use between Earth and space, create value at the same time, and solve these really challenging problems that we have? Which brings us back to Earth, to the terrestrial construction systems. I'll speak towards how and why we're creating the wall systems that we do, and also some of the regulatory implications of permitting 3D printed structures today, since it is still perceived as an emerging technology. It is an emerging technology, yes. So this is our Vulcan system. I mentioned it's a gantry-based construction system. It operates on rails. We have 2 towers as well as an X-beam that essentially have been designed and engineered to fit within a shipping container. The height constraint of Vulcan is something to note, but again, this was a system that was specifically engineered for single-family detached housing. So we weren't looking at multi-story construction at the time, and we weren't looking at multifamily, for example. In regards to wall systems, within a typical stick frame construction system, you have multiple trades and multiple, let's say, materials and finishing items that you need to complete what your wall system is and create a weatherproof building enclosure. And the important thing about each one of these elements is that they have to be done in sequence. And so if you have a delay out on site by one of your trades, it delays the entire construction process. There's no way of really optimizing that when you have these disparate trades showing up at different times. You compare that, and so what we're looking at, this is, forgive the marketing speak, but we're looking at an R13 wall, typically no wind ratings, no fire ratings. There's potential for stick frame construction to be damaged by termites, damaged by mold, and it rots in water. Not very good in coastal regions or areas that are prone to flooding and hurricanes. Whereas, in contrast, We've developed a unified material and structural system with our 3D printed wall. Effectively, the material itself is the structure. We create formwork for structural cores within the wall system itself. It's a system that maintains high thermal mass. Our lowest R rating is basically an R22. We can create more thickness, add more insulation in the wall for it to go up to like an R40. We have a 200 mile per hour wind rating. It's 2-hour fire rated, termite proof, mold resistant, flood resistant. So it's a way more resilient system. And of course, we're working in concrete, so you can, the advantages are there, of course. When we started out investigating what architecture and building performance was at ICON, we realized that we need to merge many disciplines together to really address the problem of how you build and how you create wall systems and building enclosures using 3D printed construction. And so it was important for us to consider not only design, but also building science and performance, structural engineering, because this is an inherently structural system, regulatory affairs, so that we can actually introduce a viable way for our system to be built in jurisdictions that know nothing about 3D printing, and design technology, which is essentially how you translate your design intent into functional G-code that the printer understands, but also permittable drawings. So a little bit about the wall system. In this animation that you see here, you'll notice that there are various types of reinforcement that are being added within the wall system at various points in the print. We have the capacity to include electrical as well as plumbing rough-in within the walls, and we've started to introduce a standard set of details for how we finish openings and create roof-to-wall connections. But essentially, there is a cavity with insulation within the wall. I'll let it run again so you can see a little bit better. We have horizontal, vertical, as well as transverse reinforcement within the wall. So this is truly a building assembly and not just a single material that gets printed like on a desktop 3D printer. And we work to resolve various architectural conditions within the prints for every project we encounter. We pursue various certifications having to do with the 3D printed wall. Some of those are from ICCES, in particular. The AC 509 is one of the most well-known appendices that's been written for 3D printed construction. We're compliant with IBHS Fortified, and we pursue many certifications in sort of like in improving confidence in the system so that we can build nationally and hopefully globally in the future. When we're pursuing these certifications, we do a lot of destructive testing in third-party labs with our walls. These are some examples of compression testing and plane shear, flexural testing, and then also we do wind and impact testing with our wall specimens. And every change to a wall system requires a whole slew of testing. And so you start to get a sense of just how monetarily intensive and demanding it is to create wall systems that have these certifications. That's a huge barrier for new systems, new technologies within architecture and construction. These are some of the regulatory bodies that we contribute to in subcommittees and making recommendations for standards. And the truth is that there's no internationally accepted building code for 3D printed construction today. Currently, the way that we are permitted in most parts of the United States is through a provision within the IBC that specifies that it can be up to the judgment of the building inspector to determine the soundness of the engineering and the construction. And so what that means is that typically we're providing a lot of engineering data, a lot of testing data to everybody that every city that we're permitting within. The alternative to that is to refer to the ICCES AC 509 certification, which is kind of like a product acceptance criteria that has been reviewed by ICCES validating the quality, strength, effectiveness, fire resistance, durability of the system. We have a long, long way to go before every jurisdiction accepts AC 509, and who knows, there may be new standards in the future that kind of update that or take that to the next level, I'd say. I'll speak to a couple of project examples very, very quickly just to give you a sense of the scope and scale of things that we've printed in the past. Community First Village is a project that's very, very meaningful to us. It's a community based in Austin, Texas that caters exclusively to formerly homeless individuals. And so our first project with them, we delivered a welcome center as well as 12 homes, and these homes were all printed, several at a time, I believe 3 at a time, and they're all still occupied by their inhabitants. We're very excited about that. It really just goes to show that at any given point, we're very invested in demonstrating how the technology can be used to create an impact in affordable housing. That's something very near and dear to our hearts. New Story, Mexico, we completed some homes for a community in need in Nacajuca, Mexico. These homes, interestingly, withstood a 7.4 magnitude earthquake. We were connected with a community in need with New Story Charity, who was on the ground in Nacajuca identifying what the needs were of the community, and it was a wonderful collaboration. This is ICON's first and only international project, global project, I should say. About 2 years ago, we announced House Zero, or I should say unveiled House Zero. This is the first of ICON's exploration series of architecture. Essentially, it is a self-funded project where we took it upon ourselves to ask, what is a home, what is a design that can only be 3D printed and that cannot be built through any other means or methods of construction? ICON hosted a competition. The design that was selected was by Lake Flato Architects. So you can see here, this is what we collaborated with them on over the scope of the project. Lake Flato had never designed anything with curves until they met us. But yeah, you can see that there's this wonderful blend of mid-century modern ranch aesthetic with undulating and more organic single curved surfaces throughout the home. This is the master bedroom in particular. It really showed, I think, this was a moment where we were able to show to the public that 3D printed construction is not brutal, that it doesn't have to be cold, that it doesn't have to be typical. It can be elevated, and it can aspire towards really wonderful things in terms of a combination of materials, textures, light, and experience. Effectively, this home is available for people to visit in Austin, Texas, and we use it as, again, our showpiece for what's possible using 3D printed construction. In contrast to that, Wolf Ranch is our largest project to date, and one in which we collaborated with the Bjarke Ingels Group to reinvigorate a housing collection by Lennar, who's one of the largest production home builders nationally today. Currently, we are nearly done, I can't say how many, but we're nearly done with all the 3D printing in the community. And overwhelmingly, Lennar, who's intended to finish the homes and complete the roofing and do the finish out, is taking much, much longer than we are. However, these homes are for sale. And so if you know anyone who is interested in a 3D printed home in Georgetown, Texas, there is absolutely an opportunity to purchase one. Here you can see we had 8 printers deployed simultaneously to complete this project, 2 operators per slab. It really, at least in my experience, I haven't seen a larger display of robotic construction happening on site at the same time at this scale. People have said it's the cleanest construction site that they've ever seen, and so that's something that we really take a lot of pride in. Each of these slabs represents a 1,700 to 2,200 square foot floor plan. Took about 2 weeks to print the vertical wall system of each home. And then finish out by Lennar would happen traditionally on the order of 6 to 8 months. So there's a drastic time difference there. This is a rendering of the interior of the Wolf Ranch homes, and then this is what they actually ended up looking like. So the homeowners who've already moved in are basically living on an active construction site, and what they've told us is it's still the quietest community they've ever been in. It's kind of remarkable to think about it that way. Disaster resilient housing. We've completed some homes that were promised to folks from we've completed some replacement housing for homes that FEMA promised to individuals that lost their homes in hurricanes and then never delivered, unfortunately. We were accepted as a part of their resilient housing program to provide replacement housing. Again, a very, very meaningful application of the technology to families that really never thought that they were going to have somewhere to live again. And this is all on the Gulf Coast of Texas. We've also done quite a bit of work for the Department of Defense, in particular creating barrack structures, which are transitory training facilities for troops. And these are some of the interiors as well as the exterior of those facilities. Initiative 99, I'll speak towards this as well as some of our newest and latest technology products, and then I'll hand it over to Julian. Initiative 99 is a global competition that we started 1 year ago to really ask the question from students and professionals worldwide, what could be a solution for a home that can be 3D printed and deployed all over the world to address various needs when it comes to global housing. And the prompt that we gave to the contestants was, can you design that home that can be built for under $99,000? And so we assembled a jury of a really remarkable jury that evaluated the designs over the course of 2 phases. In the first phase, we received over 300 entries from 60 different countries all over the world. Maybe some of you. Did anybody compete in Initiative 99 here? Maybe. Sorry. Well, the awards were just announced for Phase 2 this past week. These are some of the winners from Phase 1. You have a design for New Zealand, a design for Bogota, Colombia, a design for Berlin, and in the student category, a design, I forget where that one is. I think it's in Peru, a design in Berlin. And what we've done in the second phase of the competition is ask these contestants to adapt and adopt their designs for construction at Community First Village. And 2 of the winners are actually going to be built this year, which we're super, super excited about. We made a promise to ourselves that we did not want to do a paper architecture competition. We have enough designs coming at us, like we can come up with our own designs as well. We were very committed in showing how this work could actually be put to good use and can be deployed in the field in short order without waiting many, many years. So a couple of product, I guess I could say, a quick product review, and then I'll hand it over to Julian. Just this year, we're always developing our technologies in multiple areas: software, architecture, advanced materials, robotics. This year we announced a couple of, we get asked a lot of the times, can you do multi-story? Can you do infill? Can you do more eccentric geometries? And so Phoenix became a solution and a way of addressing how to create those more eccentric geometries, but for a fraction of the cost as it takes to deploy Vulkan. And so you see we are working with this robotic arm form factor. This is a demonstration structure that we created to actually show what's possible using Phoenix. It's right outside of our headquarters in Austin, Texas. And the most important thing for us, again, is to really show and demonstrate how we can create this freedom of form through the design, through the architecture, through the structure. We've also developed a low-carbon concrete material that we're referring to as Carbon X. We're well aware that concrete does not have a wonderful reputation when it comes to carbon emissions globally. I think some of that has to do with how ubiquitous it is, but in any event, it is very important to us to develop material that can be more sustainable and that can reduce the carbon impact of our work and our construction. So we're working largely with geopolymers in developing Carbon X. I would say that our next challenge is to create a more affordable and more competitive material that can be adopted worldwide. But essentially, this is the material that we're using on all of our construction moving forward. It demonstrates our commitment to sustainability over everything, really. And then lastly, or I should say second to last, we've introduced a platform that uses natural language processing to rapidly improve and I would say enhance what design innovation and ideation looks like for 3D printing. There are a lot of image generation softwares out on the market right now that are using AI and machine learning to create images, but we asked ourselves, can we create a platform that is unique and specific to 3D printed construction and that can also create build-ready plans that are 3D printable with our system? And so this is some of the work that we're developing in the future, and there'll be lots more to share about that in coming months. And lastly, we also announced this year a digital home design catalog. A lot of the times people come to us, developers, cities, and they don't know where to start. They say, you know, we don't have hundreds of thousands of dollars to invest in design using a firm, but however, we want to create a subdivision. We want to create some kind of neighborhood or community using 3D printing. And so what we came up with is Codex, which is essentially an online catalog of 3D printable designs that can be used in an open source way, truly, by others within the construction sector, and also as a starting point for us to imagine new communities and subdivisions with our customers. And so Codex hosts many collections, and it will continue to expand over time. We're actually super interested in how we can use and collaborate with folks outside of ICON, architects, students, engineers, to think about what 3D printed construction should be in the future, and then continue to expand this catalog as a kind of platform for construction, again, in a very open source way. And with that, I will hand it over to Julian to go into more detail on Codex.
Okay, thank you, Melodie, and thank you, Skylar, for the invitation. And as Skylar mentioned, I was a student here, so I'm moderately nervous about being in this room right now. I presented several projects here to what can only sort of generously be described as mixed reviews. So hopefully you guys will be a slightly more forgiving jury. This is an example of the type of Codex collections that we have generated. And by the way, before I go through all the design work that's in here, I used to work as a project lead at BIG, and a lot of the design that you're going to see here was done as part of that job, even though now I'm the director of building design at ICON. These are two of the Codex collections that we produce. One of them is to build homes in fire-prone regions, and another one is to build homes in storm-prone regions. Why? Because as Melodie explained earlier, our wall system is performs really well in both of these conditions. So this is one of the homes that we designed for the fire-prone regions. This one's we call Bend. So you can see as a kind of concrete shell that would protect it from from fires, and it has these kind of moving shutters that can protect it from fires as well in the case of a fire event. Another thing that is extremely important when you're designing for a fire-prone region is landscape. So you can see here that we took care also of designing the landscape to make sure that the house does not come into contact with fire. You can see the home here. So these homes are to be built with the printer that Melodie showed last, the boom arm printer that can print up to 27 feet. In the interiors, there's another version of a home to be built in a fire-prone region. So it has this kind of concrete shell and a protective sort of gate or door that closes in the case of a fire event. So you can see it from the side. And it generates this kind of really nice indoor-outdoor space that is quite vulnerable to fires, but it's able then to be closed during the fire. You can see the top of it. And then we also produced a collection for storm-prone regions, right? So we did a lot of analysis on what kind of shapes and forms would be best suited for these regions to resist the wind forces, water, and all sorts of stuff. And then so we came to the conclusion that in order to respond better to your wind pressures, wind forces, and all this stuff, a more sort of circular or aerodynamic architecture would work best. And so all of the forms of the collection that comes later on the storm collection are informed by that. So you can see here, for example, that the homes are not only more kind of segmented, you don't have such large surfaces, and they're all much more broken up on the roof and as well as on the rooms. I'm going to show you guys a pavilion that we built in Austin. So this is a performance space that we built in the Long Center in Austin. So all 3D printed and built as a way to publicize our shared project that we have with Icon, Big, and El Cosmico. So this is called the Cosmic Pavilion. El Cosmico is a hotel that's located in Marfa, where we will be building not only the hotel, but several homes. And this was the way to sort of show everybody the language of that the hotel would have and explore what is possible through the 3D printing. So you can see all of the geometries that are super expensive, very difficult to do with a different system, but we were able to achieve with printing. So a lot of curvatures and a lot of angles, overhangs, and things like that would require, if you try to do this with typical poured concrete, you have to think about what you're going to be building, your formwork, all of this stuff, like how you're going to reinforce it, all these things. It's a lot easier to do it, and then a lot easier to do it with a 3D printer. So it enables us to create architecture like this without the expense of having to build it essentially twice. And this is the hotel that we were talking about. I don't know if you guys are familiar with Marfa or El Cosmico. Some of you probably have gone there. I know Mateo's been there. And so it's a huge hotel, very sort of hippie-like. And these are the type of dwellings that we have in the hotel right now. And what we're doing is that we're printing the entire updated hotel in a site nearby, where we're building not only the rooms and the cabanas and everything, but also all of the amenities and the pools. So you can see here a couple of different room types and the bed for one of the roof types. So again, another thing that's possible that is enabled by 3D printing is like the ability to build in a lot of furniture and a lot of different features. Takes me to the homes that we are building. So this is called Sunday homes. We're building these homes currently in Marfa. You can see they're built or they're designed to have kind of a modular sort of idea where you create one perfect bedroom and then you multiply that bedroom or reorient it and organize it in different ways and combine it with different sort of kitchens or different modules for living rooms, etc. This is how the houses look like. This is how they look on the inside. And this is how our work site looks like right now. So you can see the printer out on the, in the middle. It's kind of very small, but you can see it. And then when looked at from above, it looks like this. So we're quite far out in the desert. The project that Melodie mentioned is the Mars Dune Alpha. So it's a Mars, simulated Mars habitat. So it's built by NASA in order to study how people will live in a long duration mission, right? So how will people live in Mars? Not necessarily how we will build in Mars, but how will we live in Mars? So we built this. This is of course a render, but we built it inside of a hangar in the Johnson Space Center. And what was really important to us was to make sure that the people living there, because astronauts are going to be living there for a year, isolated from everybody other than themselves, right? So they're going to be living here and simulating the kind of communication lag that you would have if you were living in Mars. So if you say something right now, you're going to have to wait for another 20 minutes for that something to get to Earth and then come back, right? So they're quite isolated. They don't have contact with anybody else other than their 3 other crew members. So if you can imagine sort of living and working and doing every single thing, playing, watching movies with your roommates for an entire year without being to go outside. So that is the kind of study that they're undertaking right now. So for us, it's really important to be able to separate the moments of being in a private living versus the moment of living and being sort of social and being outside, sort of talking to other people. So we split the plan into 3 different bands. You can see here, private living, shared living, and work. And then the plan was just organized based on those principles. So you can see how it transforms. You have all the super private stuff in here and the more work stuff on the other side. So that if you don't want to be social, then you can just sort of stay in your room, go to the washroom. You don't have to see anybody for a couple of days if you don't want to. Some of the interior shots of the habitat. The first mission was already took place. So the first set of 4 astronauts that lived there for an entire year just came out in the past few months. This is what we were printing. Melodie already showed like a really nice video of this earlier. This is the simulated mission, the folks that were in the mission and the crew. And they put out, actually, the Johnson Space Center puts out podcasts where they talk about all the stuff that's going on in the center, all the stuff that's going on with space. And they, every month, the crew of the Mars Dune Alpha would sort of give everyone an update on how they're doing and what's going on. Sadly, they never spoke about the building, which is kind of, yeah. And this is how we think it would look like on the surface of Mars. And then the last project that I will share with you guys is the Olympus habitat. So Melodie spoke a little bit about this project, and this is essentially what we were pushing for that machine to be able to build, right? Like what we thought it could be. So how do you build something on the moon? You have to learn from Earth vernacular. So how do we build shelter in the Antarctic, or how do we build shelter in the desert? So the way that we do it is that we use whatever is there, and then that's our construction material, and then we evolve from that. So with that as a conclusion, then our building material on the moon is going to be a lunar regolith. And lunar regolith has all of these kind of insane characteristics. A huge one being that it's incredibly abrasive, right? So how do we treat all of this? And then the sort of laser sintering that Melodie showed you guys earlier is going to deal with this material. So, and that's the goal. And then so once you start dealing with regolith as your building material, kind of lunar vernacular emerges, where it's really melted regolith that becomes your main building material. So with that in mind, how do we create a habitat that would work under those conditions? So if you think about an inflatable structure ideally would have to have a round section so that the pressure is evenly distributed. And the ideal section for a 3D printed structure that's only 3D printed would be triangular, where the angles of the walls match the maximum angle of overhang of your print. I'm assuming that all of you here have printed something at some point, right? So you know what I'm talking about when I see the angle of overhang. But what we did is that we created an optimal section that accommodates both a pressurized structure and printed structure. And then for the overall shape, we built on a lot of the studies that have been done about what is the optimum geometric shape to accommodate the maximum amount of space, not only in terms of square footage, but also in terms of volume. And these are some of the images that came out of that and some of the design that came out of that. So this is our habitat here on the left. These are some studies on what a landing pad could be. So landing pad here, that has replaceable tiles, of course, and is a lot more densely printed and populated in the center where most of the blast is going to come from, and then sort of disperses as you go outside. You can see some more images of that. And then some eye candy for the astronauts. We're looking back at their habitat. And then that's it for us. Yeah.
And I have one online. Please share more about the typical concrete mix. Does it include any post-consumer waste, and what is the typical embodied carbon content of your mix per kilogram or pound?
Oh yeah, we can
Let's
see
go
it
sit over here so that they can all see us. Okay, the first part of the question, remind me. Now that we're working with geopolymers, that's as close as we get to kind of like renewable materials, but other than that, no post-consumer waste. I would say that, well, it's a calcium carbonate-based material. So it is a mortar-based cement. It is not like pure cement. And that's to actually ensure that the rheology of the material can actually get pumped through a hose and then down the nozzle and then set with enough time to be stable enough to actually cure with enough structural support for the next layer to come on top of it. So for us, it's very challenging. We refer to it as lift time. It's very challenging to create a material mix with the right additives and mixtures based off of the ambient kind of environment that you're in that can withstand those conditions and introduce just the right amount of lift time to create your structure. So as much as we want to experiment with new materials, there's a lot of testing that goes into making sure that they're like foolproof and that they can be validated for construction. So no, we haven't done too much else when it comes to like materials engineering, apart from ensuring the flowability of the material, the rheology of the material, as well as its structural properties, and then sustainability, of course.
How much do you have to adjust for the different sites that you build on? Is it constantly adjusting?
It's constantly adjusting. In the early days of Icon, we didn't have automated admixture dosing. But today we have very sophisticated machine learning algorithms that can tell you what the humidity is, what the temperature is, and then automatically create admixture doses that make sense. But we didn't have that at first. So we would go into certain environments, it would print fine in Austin, and then we'd go to Houston and things were a disaster. And yeah, that's just one of those things that you kind of iterate on in developing the technology over time.
Yeah, so if I can speak that. So essentially the printer has a set of sensors that will tell you, or will tell itself, like, hey, it's this humidity, so you're gonna need to add this much water. It's, you know, that kind of stuff, and that's what Melody was talking about, where it's automatically sort of matching the requirements of the environment.
Thank you. So just to echo on that question, I was wondering, like, since you said you have a new type of concrete mix, which is called Carbon X.
Yeah.
Yeah. So what's the percentage of like carbon reduction it has compared to the current concrete mix you're using? If that's, I'm allowed to ask that.
Great question. So the material, we did a couple of studies on the material, and then it was independently, semi-independently evaluated by actually MIT's Concrete Sustainability Hub. And what we discovered for our typical wall system, which is a two-bead wall system, that the carbon impact is basically less than that of a stick frame construction home. So we were looking at the whole home construction, but that's what we basically discovered. That was the result of the analysis.
Hi. First, I just want to say I really like your shoes. But in the beginning of the presentation, Melody, you presented like an image of the business structure of like the modalities in which like Icon works in terms of like design and construction. But it's really interesting to see that along with a lot of work and innovation, you guys are doing a lot of social justice work as well. And I'm kind of interested to hear what that diagram looks like with a different frame of reference from the values of like, typically you don't see a lot of innovation with also a lot of social justice work. And I'm interested how that plays a role in terms of choosing projects, how like even the business of the company works and how you assert like resources in different areas?
Oh, it's a wonderful question. I think that the thing that, in my opinion, I'm biased obviously, but in my opinion, the thing that sets Icon apart is that we're not only interested in accessible and affordable solutions, resilient solutions that can perform well structurally, but most importantly, we want to create dignified housing. Like that was a key ambition of Jason Ballard, the CEO of Icon, is not to create housing that looks like, feels like the cookie cutter subdivisions that you see when you work with like a production scale builder. And so that was a key thing for us. And, you know, we really feel that in order to demonstrate that the technology is being put to good use and that it's being, I guess you could say, brought to the communities that need it most, that we have to pursue affordable housing and we have to pursue projects where the prices are not mass market. And so I've been with Icon for 4 years, and at any given point, we have at least one affordable housing project going on, whether it's at Community First Village or elsewhere. Is it a challenge from a business perspective to argue for that all the time? Of course. It's always a challenge and it's a struggle and it's something to advocate for. But so far we've been doing pretty good.
Yeah, if I can add to that, you can, if you look at the projects that we both shared, the walls are the same, whether you are doing a home at Community First Village in Austin, which is for the formerly homeless, or if you're building $4 million home, you know, like House Zero, for example. And so the goal was always to think that if this technology is good for these folks, then it has to be good for these folks. It has to be the same.
Over here. Thank you very much for the presentation. I'm curious if you've found that there are problems that you've yet to solve in the way that the 3D printing happens on a structural in a manner. For example, I noticed that the roofs and the renders were 3D printed versus the roofs and the built versions were add-ons, and some of the mantelpieces above the windows were also structurally different. So I'm wondering how you solved those moments that in the architectural sense.
I can start and then, yeah, okay. So a lot of the renders that you saw are designs that are looking at the future and looking at what we will be able to build with our second generation of printer, which is the one that Melodie showed, the boom arm that can build up to 27 feet. And so that's more where you see the difference, though it is a challenge, of course, to 3D print a roof. And then I think that's it from me.
We have many structural challenges to continue to I guess we could say expand and develop our capabilities towards. There's no, to my knowledge, there's not like a proven seismic system for 3D printed construction as of yet. I haven't seen one at least. Looking at like how we can create a continuous structure using 3D printing is a challenge for us. Insulating that continuously printed structure is a challenge for us, and creating all of your plumbing and electrical rough-in using eccentric geometries and double curved surfaces, like that's a challenge. That's not, you know, something that there's like standard protocol for, let's say. We're always looking at how we can make more cheaper and more effective foundations. And we have a very heavy wall system with the material has a lot of density. So people typically are not expecting the kind of foundations that we have to engineer for our structures. And so we're looking for new creative ways of how we can provide solutions to that too. It never ends. There's no shortage of challenges when it comes to this work.
One last thing is we are coming up with the language, architectural language, the structural language, all the language that you need for something that has not been done, really, which is building houses with this system at a mass scale, building buildings with this system at a mass scale. So every single challenge that you both enumerated is a challenge, right? Because we're just trying to come up with it. What is the best solution for this? And as you saw in Melodie's presentation, it's not just resolving it, but also getting people to approve it. There's a huge process behind, okay, a wall that you want to put in a house. So it's not just the design, not just get your structure engineer to be like, yeah, this probably stands up. It's also you have to go and show 100 other people. So it's very challenging, but what's exciting is that there's something that we're coming up with, right? We're inventing it. And so it's very forward-looking, so it's not challenges as in like, oh my God, what are we going to do? It's more like, okay, that's great. We get to invent with a better way of doing this.
I'll be quick. And then, congratulations. Obviously, you guys have scaled and you're doing so many different aspects. So fascinatingly, right, like decades ago when steel was starting up in the construction industry and you're at the sort of nascent time of 3D printed concrete, everyone before us had all of these different alloys and different processes. So you had different companies developing their own things, like Bethlehem Steel had the Bethlehem Steel Design Guide, and then all these other different steel companies had theirs. And then standardization happened, and there was a steel code and standard steel sizes from which society benefited, right? Because suddenly there was standardization across everything, and we've got a bunch of steel structures and anyone can design it. But Bethlehem Steel ain't around anymore. So my question to you guys is, because you're innovating so well, and there's obviously less innovation in steel today than there used to be, how does ICON continue to innovate, continue to expand, But then as relates to potentially standardization, how do you not become the next Bethlehem Steel?
I can start, and yeah, okay.
And I don't know either, so this
Yeah.
is not supposed to be a trick question.
No, that's interesting. How do we continue to expand? What first is, as I was saying, this is all very new, right? So we're just starting, and we're actually doing both at the same time, which is pursuing things that have never done before, but also establishing things that are going to become standards, at least for ourselves, right? And so we're going both avenues on that front. Like, okay, so what would be a standardized window detail, for example, right? But then in another project, it's like, okay, we need a very specific type of geometry to match with it, and so it's a different type of challenge, right? So from my point of view, I think we're doing both, pursuing the efficiencies of standardization. We're also establishing the standard ourselves, right? There's like not that many people that have this kind of scale and ability to test out their printing capabilities at a mass scale the way that we're doing it. And so, yeah, we're establishing standard, but also sort of deviating when we need it for to sort of expand the language of what's printed.
Thank you for the question, Paul. I love it. What Julian's saying is exactly right. What being a hardware provider, we basically have unlimited access to printing, testing, mocking up specimens and testing them, which unfortunately, I mean, not to say that it's competitive, but sometimes when we encounter academic institutions in standards organizations, they're so cautious because they just don't have the data that we have, and they just don't have the evidence to support the kind of recommendations that we're more willing to take and the risks that we're more willing to take. When it comes to like our engineering design guidelines, for example, it referenced the wall systems. There's nothing that we want to hide. In the end of the day, the only thing from an industry perspective that all additive manufacturing providers are secretive about is the material mix. Like that's across the board. But everything else, like the building assembly itself and how you build and what the construction sequencing is and what those materials are, like it's all open source available online because that it truly is like a construction system, you know? And so we want that to be adopted. We want others to expand on that. We want others to work with it so we can all acquire more data and for this construction system to be something that can be deployed everywhere. So on the one hand, you know, I think this is just an example of how being vertically integrated presents such an advantage to us. Because I don't know if Bethlehem Steel like was forging their own materials, or who knows where their stuff was coming from and what the supply chain was in the end of the day. We're trying to streamline as much of that as we can so that we have a direct impact on what it is that we're producing and engineering. And then for sure, we want there to be standardization across industry. By and large, anyway, I'll just say that.
I don't know if I mentioned once again. I don't know if I mentioned either of us mentioned it before, but we also have an architect's handbook that already sort of takes a step at kind of giving everyone the tools that they would need to design with the system. So.
I'm curious, what was the material in the Mars project? And I'm asking because it was reddish, and was it a design decision or a material decision? And how do you imagine the real material on Mars? Because I'm guessing water is a challenge there.
I'll take the first one. Okay. So the material is essentially the same material that we would use, that you saw in all the other homes and every other printed structure. It just has pigment to it, right? So we have pigmentation, and that just goes to show the variety of colors that you can reach with the printed material. You can change your pigmentation to be either that or like much darker or black, all this other stuff. So the material was pretty much our standard material with a pigment.
Yeah, it's kind of superficial, but it was fun. It looks more Mars-like, right? um, and then in regards to actually 3D printing on Mars using Martian regolith, you're absolutely right. Like, there's an open question as to whether we want to use like heat-based methods or whether we want to use concrete and rely on hydration and curing of the concrete. So there's a couple of questions there, like where do you get the water, right? And are you going to have a sufficient supply of subsurface water to actually create your material? And then on top of that, what does it look like to cure in Martian atmosphere? Certainly you couldn't do that in a lunar environment, but perhaps with the right material you could on Mars.
One cool thing I just remembered actually. At the Johnson Space Center, they created a sort of sand bed around the habitat. Remember? So it's like so you have the habitat, and they just put a bunch of sand around it, and it's really red sand. And so now and they really match the sand of the that they have around it and the red of the habitat. So we kind of we nailed it in a way unknowingly.
Coming back to the affordable housing question, it seems as though time to create or construct and cost are key considerations. But could you talk a little bit more about the life cycle cost, whether that be associated with repairs and with materials and forms that local communities may not be as used to working with? And then if you can talk a little bit about future modularity with existing projects. Yeah.
Okay, so I'll talk a little bit about how we can fix it, and then pass it on to Melody. So, you have a homeowner's manual that sort of shows folks how to fix the like if anything happens to the wall. I mean, you can imagine concrete wall. It would be quite tough to damage it. But the second portion of this is that if you've ever had a kind of flood in your house, in a I don't know, all of you guys have probably ever had some plumbing problem, right? And then it turns out you have to cut all of your drywall, all of that stuff. You have to cut all of it, and then you have to go back and rebuild it, right? The same way that you just sort of learned to destroy. This does not happen with the Icon system, right? If you have a flood, then you you clean it out, and that's it. You don't have to rebuild the same thing over and over again. And so, from that point of view, the life cycle of the home becomes a lot sort of longer, right? You're able to live in the same place with the same thing, same materials for much longer, much more resistant, essentially, to any kind of damage. So that covers the life cycle portion, I guess, of the question. And can you repeat the second portion? Modularity. Oh, yeah.
Modularity in regards, could you elaborate on that? Sorry.
Yeah, happy to. I was more thinking about like expansion, if possible. Should there be, I don't know, you move in with, you have a grandparents move in, or you have a multi-generational home. Is this something that is able to be done post fact?
It's a great question. Certainly with the Vulcan system, that is a shortcoming, right? Like doing renovation, doing infill, introducing like expansion or adaptability of existing printed designs is not easy and frankly not feasible right now. It is a specialty system, right? So a lot of times people say to us, well, what if a car runs into a 3D printed wall? I'm like, well, what are you like? What are we gonna do about that? In the end of the day, we have, we have methods, and we also have guidelines for small repairs and general maintenance. But it is a specialty system. It is very hard to duplicate the look and feel of the beads, and for us, the cosmetic repairs are very achievable. But it's the larger structural changes which would require an engineer, which would require rework, and that is a more complex thing, which we're starting to think about answers for, but it's a few years out, let's put it that way.